Welcome back, everyone. We've all heard the pitch, right? We need to completely overhaul how we travel if we're going to save the planet. But here's the thing. How much of what we accept as gospel about green transportation is actually the whole story? Today, in this explainer, we're pulling back the curtain. We're going to unpack the real, hidden environmental footprint of the vehicles we drive every single day.
Think about the ultimate universally accepted symbol of clean transport. It's an electric vehicle, right? Cruising silently down some lush green coastal highway. And man, the narrative is super compelling. You buy an EV, you stop burning fossil fuels, and boom, you're immediately living in perfect harmony with nature. It feels fantastic. No smoke, absolutely no noise, just a perfectly smooth, clean ride straight into a sustainable future.
For years now, we've framed the choice as this simple black and white binary. On one side, you have the clean, futuristic plug of an EV. On the other, the traditional and, let's be honest, kind of dirty act of pumping gas into an internal combustion engine or an ICE vehicle. We've treated this basic side-by-side comparison as the absolute alpha and omega of environmental responsibility. Basically, you plug in, you win. You pump gas, you lose. Simple, right? Well, what if this comparison is actually leaving out the most crucial parts of the entire story?
Which brings us to a massively important question. Are EVs actually greener? It is time we pivot our perspective on this. Zero tailpipe emissions do not mean zero emissions across the board. In fact, what comes out of the back of the car, or doesn't in this case, is literally just the tip of the iceberg. To truly grasp the environmental impact, we have to look way beneath the surface.
Because the true environmental cost of an EV, it's often hidden in these invisible burdens. First up, you have the incredibly intensive extraction of critical minerals required just to build those massive batteries. Second, you got to look at the electricity grid itself. I mean, if you're plugging your pristine, clean car into a grid that's heavily powered by coal, how clean is your commute really? And third, the actual manufacturing processes for EVs are vastly more complex and way more energy heavy than building traditional cars.
So here's how we're going to unpack the data for you today. We'll look at transport emissions, then the policy push. We'll get into life cycle assessment explained, compare the real impacts, and finally, navigating the road ahead.
All right, kicking things off with Section 1, Transport Emissions, looking at both global and local impacts.
87%. That is a staggering number to wrap your head around. Globally, the transport sector is responsible for roughly a quarter of all energy-related greenhouse gas emissions. That's a huge slice of the pie. But if you zoom in on a rapidly developing nation like India, you'll see that road transportation alone causes a whopping 87% of the total emissions within that sector. With population and vehicle ownership just absolutely exploding right now, leaving this unchecked would lead to some pretty severe environmental outcomes.
Moving on to Section 2, the policy push, and how governments are forcing a rapid transition.
To get a sense of just how fast this transition is being pushed, let's look at India, which, by the way, is the 5th largest auto industry in the world. Way back in 2013, they launched the National Electric Mobility Mission Plan. Then things escalated in 2015 with FAME I and absolutely exploded in 2019 with FAME II. That phase injected a massive 100 billion rupee outlay designed to artificially generate market demand, specifically targeting thousands of e-buses and literally 1 million electric two-wheelers. Plus, more recently, they've actually advanced their targets for blending 20% ethanol into petrol by 2023. So the policy push here is incredibly strong, leaning heavily toward electric mobility.
Which brings us to Section 3, Life Cycle Assessment Explained.
Now, to objectively measure the impact of all these policies, we use a tool called a life cycle assessment, or LCA. Instead of just focusing on what happens when you turn the key or push the pedal, an LCA is a comprehensive methodology. It evaluates the environmental impact of a product across its absolute entire lifespan. Honestly, it's really the only impartial way to fairly compare vehicles because it measures everything hidden below the surface.
So the crucial thing to understand is how this life cycle is actually broken down. It essentially happens in 4 distinct phases. First, you have raw material extraction, literally mining the stuff out of the earth. Second is manufacturing, putting the battery and the vehicle together. Third is the use phase. That's the driving and charging part we're all familiar with. And fourth is end of life. Basically, what happens when the car finally dies. Keep this firmly in mind as we go. Energy is consumed and emissions are generated at every single one of these 4 steps, completely regardless of the vehicle type.
Let's dive into Section 4, comparing the real impacts, specifically looking at IEC versus EV trade-offs. When we break down these trade-offs using standard recipe impact categories, the results are actually kind of surprising. Let's look at global warming potential. ICE vehicles obviously spike during their use phase, the tailpipe emissions, but EVs, they actually spike way earlier during manufacturing and grid charging. Now, EVs clearly win hands down on freeing us from fossil fuel dependency. But on the flip side, traditional cars actually have a much lower impact when it comes to mineral scarcity and water consumption. So as you can see, it's definitely not a clean sweep for either side.
And that mineral scarcity? It's a seriously heavy burden. An EV requires massive amounts of lithium, cobalt, and nickel. Extracting these critical materials from the earth is an incredibly energy-intensive, water-heavy, and frankly, disruptive journey. Because of all this, an EV begins its life on the road with a vastly larger initial environmental footprint compared to a standard traditional car.
This creates what experts call a carbon debt. Think of it like this. A standard gas car takes relatively little energy to build, but its use phase emissions grow massively over time. And EV is the exact opposite. It starts out with a huge chunk of manufacturing emissions. That is the upfront carbon debt for mining and processing all those battery minerals. Then, as you drive the EV, its use phase emissions grow much slower. This allows it to eventually pay off that debt and become greener overall. But that payoff relies on one massive assumption, which we're going to talk about in just a second.
But before we look at the power grid, we really need to look at the end of the road. Because of that intense upfront mineral investment we just talked about, the end-of-life phase for EVs is absolutely critical. Proper recycling, specifically recovering those precious metals through what analysts call substitution and cutoff approaches, is literally the only way to ensure the lifetime environmental math actually works in favor of the EV. If these giant batteries just end up sitting in a landfill somewhere, the entire environmental benefit pretty much collapses.
Which brings us to our final part, Section 5, Navigating the Road Ahead, and the systemic changes we desperately need.
Greening the power grid is the ultimate prerequisite here. Remember that carbon debt payoff we talked about? Well, the environmental viability of an EV during its use phase is entirely dependent on the local electrical grid. If your brand new EV is plugged into a grid that's still burning coal, its global warming potential stays incredibly high. To truly realize the benefits of electric mobility, we have to simultaneously and massively increase the renewable energy capacity of our power grids.
See, we're really left with needing a multi-pronged approach. On one hand, EVs are a big long-term bet, but they rely heavily on decarbonizing grids and fixing complex mineral supply chains, which takes decades. On the other hand, alternative fuels like extracting compressed biogas from agricultural waste or blending ethanol into gas offer immediate parallel solutions to reduce the footprint of the millions of combustion engines that are already on the road today. It's not an either-or situation. We need the whole shebang.
And that brings us to a final thought to wrap up today's explainer. If an EV is genuinely only as clean as the electricity that powers it, what is the true footprint of your daily commute? Seriously, I challenge you to look up how your local energy grid is powered, because true sustainability isn't just about what kind of shiny new car you buy, it's about systems thinking. It's about understanding the entire life cycle of the choices we make. Keep asking those hard questions, keep looking at the data, and we'll catch you on the next explainer.